Hey guys, how's it going? I'm going to be putting a face to this YouTube channel. But today we're going to be talking about post-einsteinian gravitation. Um, what it is a strategic shift in gravitational physics. Oh wow, I just turned off the thingy. Um, but yeah, so we want a controlled enlargement of the fundamental hypothesis of Einstein in 1915, which is that the vanishing of torsion from the point set nature of an X4 as a manifold is systematically relaxing to accommodate for quantum gravitation or other higher order symmetries that we would be interested in. Um, and yeah, so as the Jet Space Institute, we're gonna view the program of post-Einsteinian gravitation as the Levi-Civita, basically general relativity itself is the Levi-Civita sector of a more expansive theoretical landscape. Okay, so that's the idea. That's the general idea. We have some goals here for the roadmap, but we're going to go through classical geometry and then studying the nature of those fields. I'm going to assume that you are somewhat familiar with the solutions to the Einstein field equations, just Kerr metrics and all these things, because that's a lot of what the experimental probes are doing. All these modern experiments and stuff, they're trying to test these solutions, these classical solutions of Einstein's field equations. And then we'll move on to continuum quantum matter, and then possibly the quantum completion of general relativity, or of post-Einsteinian, of gravity. Okay, so you have general relativity, and we're going to enlarge the Levi-Civita sector to move beyond the classical commutative point set manifold toward a geometry of string completion. You have the connection that it actually might carry independent torsion. The connection might also have independent non-metricity, and a structure group itself might actually include supersymmetry, as well as matter being treated as a quantum field whose ultraviolet behavior requires control on curved backgrounds. We'll get into this as well. And the metric also, this leads to the metric that it may also emerge as a consistency condition of a quantum string. Okay? So just this whole idea is to move the framework from these torsion and non-metricity, no longer excluding them as postulate, right? We don't want to exclude these possibilities anymore, but we want to move from point set manifolds to supergeometry, or allow gravity to be forced by supersymmetry rather than just being some optional coupling. And this represents a necessary progression into the quantum regime, where the classical assumptions of the 1915 theory are treated as a specific, highly tested limit. So, to understand where we're going, we first need to establish the precision of our current ground truth of empirical testing. There's the microscope, the Cassini probe. There's specific metrics that we use for pulsars to test classical GR. And GR remains undefeated in the laboratory. And these tests kind of bound the deviations rather than probing the geometric structures, like torsion or Reggie slope corrections or whatever, right? So, but these current results are impressive, and we can look at kind of just how much in agreement they are with this plot here. The purple would be completely agreeing with GR. By the way, I did like kind of a literature review and sourced some of these numbers together. For what GR predicts and the kind of the range which everything is at. So you have these, the microscope experiment uses spinless masses, so like titanium and platinum, but it would be silent on these extended kind of Einstein-Cartan torsion, which requires spin sources to actually manifest its effects. And furthermore, you have these detections that effectively eliminate the large class of scalar tensor models that predicted anomalous propagation speeds. But of course, the gravitational and the speed of gravitation essentially remains extremely close to the speed of light. So, in fact, they're basically the same. So by 15 decimal places. So you have like these different anomalous. I mean, the focus also moves to the Sagittarius A star results as well, that define the boundary for the next waveform type of spectroscopies, because we're trying to talk about the Kerr metric here for a rotating black hole, the classic, just seeing how much it agrees with the experiment. So while the metric is rigorously tested, the core idea is that the nature of the connection remains an open frontier. So that's why we go into Cartan geometry, where we have these more flexible dictionaries than standard general relativity, by modeling space-time on a homogeneous space that then allows us to treat the connection and the metric as independent degrees of freedom and enlarge our geometric toolkit according to the value of the cosmological constant. So you have the the Palantini pair here is, for example, you have a space-time that's required, where that's described by a spin connection and the soldering form of the Vielbein. And all these groups that come out, for de Sitter space, anti-de Sitter space, and then just like regular Minkowski space, for different choices of the cosmological constant, torsion, metric affine gravity as well. This enlarges the structure group to the general linear group, and the notion of non-metricity as well is sourced by something we call hypermomentum. So, okay, these are all interesting things, but moving to a homogeneous model where we have Cartan connections, we can identify that the tangent bundle with an associated bundle where the M component of the connection serves as a soldering form, the significance of enlarging the structure group to metric affine gravity is the introduction of non-metricity and hypermomentum. It's not just mass energy anymore. It serves as a physical source for geometry that provides a path to theories where the connections are not uniquely determined by the metric. So, you have the local structure of connections, but now what we need to do is talk about the global properties and instabilities of the Einstein metric. So, of course, there's other theories, Einstein-Cartan, there's Migdal-Mansouri theory, metric affine theory. But yeah, I mean, these are all things that can be further talked about. But let's move on to basically the Einstein equation as a nonlinear second-order partial differential equation, and understanding the moduli space, which is basically the space of all the solutions of modulo coordinate transformations, requires analyzing the second variation of the Einstein-Hilbert action, which is shown here. And it has a second variation, or transverse traceless tensors that govern the second variation of the action. It's called the Likernowicz Laplacian. And there's some spectral implications about this, because if you have a negative spectrum, this indicates the dynamical instability of the background. If you have zero modes, that represents an infinitesimal Einstein deformation. So you have these special holonomy that links Riemannian signature analysis to Kahler, Einstein, and Calabi-Yau manifolds with the SU3 holonomy. So, okay, while you have the Lorentzian Cauchy problem being the standard for evolution, the Riemannian signature analysis is vital because you have these internal spaces that define the compactification manifolds for string theory, and the stability of these metrics are determined by the Likernowicz spectrum that ensures the consistency of the four-dimensional physics that emerges from the high-dimensional geometries. Okay? So you have internal geometry, but internal geometry is only half of the physics. Okay, because we have to look outward to the boundary of space-time. So that's what we have to talk about then, conformal geometries, which is a lot of from the work of Roger Penrose. But you have conformal geometry that preserves angles rather than scales, and this is the natural language for studying gravitational radiation at null infinity. Okay, so you have you attach a null infinity to an asymptotically flat data to return global analysis into the local geometry at the boundary. There's also tractor calculus, which gives you a method to linearize conformal actions, and the tractor curvature at the boundary encodes gravitational radiation. There's the BMS algebra, where you have the symmetry of the vacuum that includes super translations. This is just kind of a nice linkage of Lorentz transformations to the infinite dimensional symmetries that you work with in conformal geometry. And then there's also the Virasoro algebra. It's a two-dimensional conformal algebra that serves as the organizational principle for a string world sheet. You have the BMS algebra that reveals the gravitational vacuum, and that is degenerate and possesses a much richer structure than the Minkowski case. But furthermore, you have these infinite dimensional Virasoro algebras that provide the primary framework for a string world sheet that effectively links the deep infrared asymptotic symmetries, right? The deep infrared to the deep ultraviolet string theories and high energy types of regimes. So, okay, now that we have the vacuum and its symmetries, what we need to do is think about, okay, well, you have particles, right? And the particles inhabit space-time, and specifically fermions do. And so what this naturally leads us to talk about is spinors and twistors, okay? And basically to include fermions into gravity and gravitation, how fermions gravitate, you have to assume a spin structure on the cotangent bundle. On the tangent bundle. Okay, so the twistor theory will take this further by suggesting that spinors are not space-time points, but actually the fundamental building blocks of reality. So you'll have a twistor space, which is isomorphic to the complex projective line in complex projective three-dimensional space, and a space-time point would then be derived as a compact holomorphic curve on the complex projective line in twistor space. So you have Penrose transforms, which maps helicity S fields to cohomology classes, and then transforms the hyperbolic partial differential equations into holomorphic geometry. You also have super twistors, where you can introduce Grassmann coordinates, where you have bosonic and fermionic data that coexist on the same space, which is very useful. So it was useful enough that I thought it was useful to include it in here. But so, you have this ontological shift, right? Because in the twistor program, you don't really solve equations on space-time. You just use holomorphic geometry in twistor space to generate solutions. Okay? So, this, marks the formal encounter with supergeometry in our sequence. And the super twistor space allows for bosonic and fermionic degrees of freedom to be handled on equal footing. And so, as these fields evolve, you have to address the quantum challenge, right, of defining a vacuum in curved spacetime. So, what we now have to go to is quantum field theory. So, of course, microlocal analysis. But first, let's just classical fields in curved spacetime. You have to talk about the semi-classical Einstein equations with the Bianchi identity and forcing the mass energy on shell to be zero, the covariant derivative on the mass energy to be zero on shell if you have a Klein-Gordon equation with the Ricci curvature scalar. Okay. This is just all that's required before quantizing. All right, let's just move on. You have a generic curved background, okay? Just assuming this. And there's no time-like killing field, and thus no preferred vacuum states. So what we need to do is require a rigorous rate to control the short-distance ultraviolet behavior of the quantum fields. So you have the Bogoliubov coefficients, and these allow us to relate particle definition between regions and result in cosmological particle production and Hawking radiation. Okay. It's kind of related to the Unruh effect, not really. In different frames. You got your creation annihilation operators in a different frame. But yeah, anyways, the Hadamard state as well as a class of physically admissible states where you have 2-point functions omega sub 2 that possess the Minkowski-like short-distance singularity. And then Sinji's world function, of course, the Vlek-Moret determinants that yield these renormalized stress energy, stress energy tensors. You also have the wavefront set. This is a very nice microlocal tool that records both the location and cotangent direction of singularities. Okay, so you have a cotangent bundle or wavefront set that's defined on a cotangent bundle that encodes the direction as well. It's kind of what's happening here. And then Radzikowski's theorem. This is a cornerstone of this entire framework because it proves that the Hadamard condition is equivalent to a specific spectral condition on the wavefront set. And that allows us to then propagate the singularities along a future directed null geodesics with the Duistermaat-Hormander theorem that provides the global formulation of quantum field theory without needing a space-time isometry or space-time isometries. Okay. So, we can consider how gravity interacts with macroscopic matter now. And that's where this is kind of the last classical continuum theory, is the relativistic formulation of magnetohydrodynamics, where you basically have the interaction of geometry with conducting fluids, okay, which is essential for understanding the high energy environments where we test general relativity. So we have ideal stress energy. We have tensor distributions that are used to provide matching conditions for shock waves across hypersurfaces. And of course the hypersurfaces assumed would be on a Lorentzian background. You also have geometric energy transfer, so gravitational waves that excite these magnetohydrodynamical modes that then transfer energy from the geometry to the electromagnetic field. And then you also have the magnetohydrodynamics just as this geometry matching problem in general, right? Where you have a gravitational wave that passes through some pulsar's magnetosphere or an accretion flow, transfers energy from the metric into the plasma, and then that's the point where the abstract connections meet the observable, so that the linear behavior become basically we get these nonlinear behaviors that happen from extreme astrophysical phenomena in the media that these astrophysical astrophysical bodies have. It's like carrying current and things like that, much like a conducting fluid. So that's kind of there's some continuum phenomena to play around with, but we start to leave the continuum for talking about grading coordinates through supersymmetry. So there's an important result called the Coleman-Mandula theorem, which tells us that if we were to mix space-time with internal symmetries, that's trivial, right? But this is evaded by using a graded Lie algebra and anti-commutators. And so in the context then, you have gravity that becomes gravity becomes no longer optional, right? Like mathematically. Because you can define something called a supermanifold where you have even and odd coordinates, or even x mu coordinates and odd theta alpha coordinates where theta squared is 0. And you can force gravity by the anti-commutator of the two local supersymmetry transformations to yield a diffeomorphism. And in n equals 1, the gravity multiplet consists of the Vielbein and the Gravitino, which comes from a Rayita-Schwinger field. That should be over here. It comes from a Rayita-Schwinger field. And so you have this consequence of supergravity. And supergravitation comes from the fact that if you have a local supersymmetry that forces gravity into the theory, you can't gauge supersymmetry without gauging the Poincare algebra. So if you're gauging the Poincare algebra, you get these supergravitational types of notions. So while the Einstein equation is recovered naturally from the supersymmetric action, the theory itself faces these kind of obstructions when you're moving to higher higher numbers for the gravity multiplets. Okay, so the obstruction of this off-shell closure allows us, or tells us, to shift to a specialized geometry of harmonic superspace. So we create harmonic superspace because standard superspace fails to provide off-shell closure for extended supersymmetry, where you have, n is greater than or equal to 2, which means that the algebra will only close if the equations of motion are already satisfied. So if we look at internal geometry of S2, this promotes the internal, special unitary matrices to a sphere. We have the special unitary matrices quotiented by the circle U1, and with naturally harmonic coordinates, u plus or minus, or u sub I plus or minus, right? These are harmonic coordinates. Now, you can also have these analytic prepotentials that allow n equals 2 supergravity and Yang-Mills to be written using unconstrained fields. And then finally, the infinite tower, where you have these expansions of the S2 problems on the auxiliary fields that are needed to couple quaternion and Kähler or hyperkähler targets. So, basically, if you move the constraints of the geometry to the harmonic coordinates, physically, what we're doing is we're resolving the off-shell closure problem, and the complexity of the prerequisite for a consistent theory that can describe the coupling of gravity to the complex matter systems is required by the extended supersymmetry. Okay, so we finally have this synthesis where we're replacing this point particle essentially with the string itself. So, in string theory, gravity is not a postulate, but gravity itself is a consistency condition of the quantum string's propagation in the background target space. Okay, where you have you have your metric tensor G mu nu, you have your Kalb-Raman field B mu nu, and your dilaton field. Okay, so there's something called where you study nonlinear sigma models, which allows us to describe world sheets. Quantum Weyl invariance requires vanishing beta functions, so that's where we have the beta sub g is equal to 0. That gives us the conditions in terms of the Ricci and orders of the Ricci trajectory. You also have dualities, the notion of dualities, which comes from over here. You're organizing the theory with symmetries like O, D comma D, and E sub n of n, which these are just like double field theories and exceptional geometries. And you can use doubled or exceptional coordinates to handle more the order of Ricci trajectory corrections or Ricci slope corrections. But okay, basically how to read this stuff, because this gets really advanced really fast. Gravity is recovered again in the low energy limit of string theory, but the string length, the square root of alpha prime, generates an infinite series of higher curvature corrections. So again, the dilaton and the Kalb-Raman field here they're linked to the metric, and the massless two-derivative graviton remains Einsteinian only in the limit where these corrections vanish. So we can continue really by mapping this this idea of supergravity, double field theory, and exceptional geometry into the experimental programs here. But let's kind of talk about and reflect on what we did and kind of why we want to keep it this way, or why I'm presenting it in this way. So you want to first relax the connection for just as the program of post-Einsteinian gravity. You relax the connection. You want to study the partial differential equations, so the global properties of the Einstein metrics, Einstein manifolds, the spectrums, and Calabi-Yau moduli. Relax and scale spin, quantize matter on a fixed background, pass through continuum media, grade the coordinates themselves, and then close the algebra off shell. with harmonic superspaces to then replace the point particle with world sheet violin invariance in the Einstein equation corrected in the Regge slope, organized by duality. All right. So you have the gravity itself as this dynamical system of connections. Okay, and the superfields, conformal field theories. The classical limit of these theories is all Einstein, and fundamentally what we're trying to do is understand the quantum completion of gravitation. Okay, that's an open problem. Now, so we have some things to look forward to. We have the parameter bounds. We don't really have to think about parameter bounds anymore for the standard general relativity types of testings. But now we're looking at waveform spectroscopy and looking at high precision instruments to test the foundations of the connection itself. So tests of the of the graviton mass, of course, extra polarizations and post-Einstein coefficients. In 2026, we have that to look forward to at the GWTC. High statistics run ring overtones in 2027, 2029. LIGO India and the Einstein Hubble telescope for polarizations and Kerr shadow refinement. We're trying to refine our measurements on the Sagittarius A star. And then also LISA and the Event Horizon telescope, Einstein. It's not Einstein Hubble telescope, the Event Horizon telescope. But yeah, we have the Cosmic Explorer as well. That'll come up as well. The Einstein telescope targets. They're basically, we have the millihertz EMRIs and the third generation spectroscopy as well to look forward to in 2025 and beyond. Yeah, as the jet space, we can think about constructing kind of a dictionary and kind of a hub, if you will, for theoretical introspection, as well as we all have access to data sets, public data sets. We all have access to Claude or Cursor, whatever you guys use. Yeah, I mean, our strategy should involve mapping the metric affine operators, or the metric affine gravity operators, or the Cartan operators such as torsion, onto the parameterized post-Einstein coefficients. That data is available. There's also public catalogs like GWOSC where we can derive extra polarization amplitudes. Furthermore, there's ground truth. So like the nanograv is like a 15-year-old PTA results. The Hellings-Downs correlation. We can rigorously test this against scalar or vector background templates to confirm the tensor nature of the stochastic background. There's a lot of things that we can do. So, and just the quantum completion of gravity is open, right? But our dictionary, we're trying to construct a dictionary to help us find it, right? So here's some ideas. Basically, just turning Cartan data into extra polarizations, and these are things that we can play around with by contributing and contribute to as well. Maybe some publications can come out of it as well. But yeah, I'm just kind of throwing this out there as post-Einsteinian physics is pretty cool, and it's something that I don't want to give this presentation for nothing, right? I think definitely we can get busy. But yeah, here's the references. Very good books here. Good results. All of the figures and well, I made the figures, but all of the numbers and the tests and everything from the experimental programs all were cited. But yeah, without further ado, I think that is pretty much it. So yeah, thank you guys for watching. Hopefully you didn't mind my face in this video. And yeah, I'll see you guys later.